Hello and welcome. In this edition of Mark's Tech Talk, we'll be looking at digital logic gates. The first gate we'll look at is the inverter, sometimes referred to as a NOT gate. This is symbolized with a triangle and a circle on the output. The circle is really important here because that really is what indicates the inversion. The truth table shows you the relationship between the inputs and the outputs. So with the inverter, the input is a variable we call A, and the output will have the opposite states. So we have digital logic possibilities of 0 or 1 binary number system. And if we input a 0, we'll get a 1 on the output. If we input a 1, we'll get a 0 on the output. So what do we mean by these variables? Well, they really represent the voltages we're applying to the gates. So a 1, for example, might be defined as any voltage between 2 and 5 volts, and a logic 0 would be between 0 and 0.8 of a volt. And that actual definition is going to vary by the type of logic family. This is a TTL logic. It also varies with the manufacturer. And there's also some variation based upon whether you're looking at the input or the output. The output is held to a stricter standard than the input. So A could be either a 1 or a 0, and the not A in the inverter is simply the opposite of that. If we look at that in terms of a Venn diagram, the left-hand circle would be A. The not A would be everything outside of that, the blue-colored area. The next logic gate we'll look at is the AND gate. This is the symbol for the AND gate. This is pictured with 2 inputs and 1 output. 2 inputs on the left, the 1 output on the right-hand side. When you're sketching the AND gate, the input side is a straight line and the output side is a half circle. The truth table for the AND gate is this. Essentially what it is we have to have a 1 on both inputs in order to get a 1 on the output. So if both A and B are high, then we get a high on the output. But this really follows through when you have more than 2 inputs, and it's possible to have pretty much any number of inputs on AND gate. 2 are common, 4 are also common. So in order to get a high on the output, all inputs must be high. We can illustrate that with a larger truth table, and you can see that all of the outputs are low or logic 0, with the exception of the last one where we have a 1 on every input, A, B, C, and D. All the inputs are high, then we get a high in the output. Any other case, we get a 0 on the output or logic low. Notice when we're doing truth tables, in order to make sure that we have all possible states, we set it up so that the zeros and ones are just as if we were counting in binary. So we start out with 0000, then we go to 0001, 0010, just as if we're counting in binary. That makes sure that we get all the possible states represented in the truth table. If we're looking at this in terms of a Venn diagram, the A is the left circle, the B is the right-hand circle, and we are looking at where both of these overlap, all of the outputs that have both A and B in common. That would be the AND gate. The OR gate is symbolized by this symbol, and you can see it is different from the AND gate because on the input side, instead of having a straight line, now we have an arc, and on the output side we have 2 arcs that meet at a point. Remember before on the input on the AND gate we had a straight line, the output was a half circle. This time for the OR gate the input is an arc and the output comes to a point where the 2 arcs meet. So make sure you differentiate that. I have a lot of students that are a little careless here, and it's sometimes difficult to distinguish between an AND gate and OR gate if you're not careful. Truth table for the OR gate, you get a high if either A or B is high. You get a low when both of those are low. Notice the symbol there, A plus B, that represents the Boolean addition. So OR gate gives you Boolean addition. And you may have seen for the AND gate, instead of a plus there, we had a little dot that indicates multiplication. So the AND gives you Boolean multiplication, the OR gives you addition. So the OR gate, you get a low when all inputs are low. And I'm not going to show you that expanded truth table. You can imagine it's the same idea. So with the OR gate, the Venn diagram will look like this. If you have a member of A or B, then that is a valid output. Then we have a NAND gate. NAND stands for not AND. And remember we had that little circle on the inverter that represents the inversion. Well, that's exactly what we're doing here. We're taking the AND gate and adding an inverter to the output. So our truth table for the NAND gate is going to look exactly the opposite of the AND gate. It's going to take the AND truth table and invert all of the output. So we have 1, 1, 1, 0. Previously for the AND gate we had 0, 0, 0, 1. So we just inverted the output. And we can indicate that with our Boolean indication by having A multiplied by B and then putting an overbar over the top. That overbar indicates the not function or the inversion. So it is not and, and then the output is inverted. Venn diagram looks like this. It's exactly the opposite of what we had with the AND. NOR gate, same thing, same idea. We have an OR gate with an inverter on the output. Represent that with a circle. So our truth table would expect to be exactly the opposite, and that's what it is. We have a 1, 0, 0, 0. Only when both inputs are low do we get a high on the output for the NOR gate. And again, the OR function is addition, and then we put the overbar to indicate the not, the inversion. Here is the Venn diagram representation of NOR. Then we have another gate called an XOR. X stands for exclusive OR, and the XOR, or exclusive OR, is very similar to the OR gate, but it excludes the case when both inputs are high. So when both inputs are high, we get a low on the output. So that's the difference between the OR gate and the exclusive OR gate. That last case where both inputs are high. With the OR gate, that would have been a 1. With this exclusive OR gate, it's a 0. Notice the Boolean symbol is a plus, just like an OR, but now we put a circle around it to indicate exclusive OR. And again, the X indicates exclusive OR. This would be the Venn diagram representation of an exclusive OR. And then here is another gate. This is an exclusive NOR. Just like the exclusive OR, we have 2 arcs on the input side, but now we've added the circle on the output side to indicate the inversion. This is not a very common gate, but it is available and you may run across it occasionally. Here is the truth table for it. Again, it's just the opposite of what we've had for the exclusive OR. We've just inverted that, so we get a 0, 1, 1, 0 on the output. So those are our logic gates. I hope you can get some better understanding based upon what we went through. And here's a little bit of a summary of the logic gates. We have the possible inputs, the symbols, and what the outputs will be. So that concludes this video, and hope you stay tuned for more videos on Mark's Tech Talk. Thanks for watching.